Hello, good afternoon. My name is Reinhard Haas, and it's a great pleasure for me to be here today in Boston and to enjoy this really nice weather. Last time when I have been here, it was snowing and my flight was delayed 3 days. So I hope and I think that this will not happen this time. It's a great pleasure to share with you today some of our ideas, Technical University of Vienna, on prospects and impediments for a sustainable hydrogen-based energy system. In my presentation, I will first shortly introduce the major problems we have today. I will next look at history, what has been already explained regarding the vision of a hydrogen economy. I present a survey on major technologies, analyze costs and economics of hydrogen, shortly discuss the environmentally benignness depending on the color of hydrogen, scenarios, technological learning, as well as policy strategy will be the further major issues. And finally, I will be a little bit critical. What if it is not feasible? What if the hydrogen economy is not feasible? And conclusions will complete my presentation. So today the motivation is we have the Paris agreements for reducing greenhouse gas emissions. We have the urgent needs to look for and find clean energy carriers. We have currently the situation that we have in many countries increasing variable renewables, and here we have the problems that we need some storage. And finally, hydrogen is seen as such a clean energy carrier, I would say already since decades, yet so far it has not delivered. The core objective of our presentation are to analyze the prospects and impediments of such a hydrogen-based system, to identify the role of hydrogen, to integrate even larger amounts of renewables into the electricity system, to analyze how efficient technical solutions based on hydrogen can be, and to investigate the economic prospects as well as the environmental ones. Let's shortly look to history. Visions of hydrogen has been provided already in the 19th century. In 1874, Jules Verne in his work, The Mysterious Island, said, "I believe that water will one day be employed as fuel, and finally it will substitute coal. Water will be the coal of the future." Next, we can see after this first vision, it took some time. In 1958, the first PEM fuel cell was invented, and 1 year later, the first fuel cell vehicle using hydrogen as a fuel. 1966, General Motors used fuel cell technology in the production of an electrovan. And let's say in the year 2019, the global vehicle stock was about 13,000 worldwide. In various countries, this hydrogen vision was already launched in different formats. In Germany, here we see from 1984, hydrogen from nuclear. It was mainly the idea to use excess electricity generated in nuclear power plants to produce hydrogen. And some years later, the idea to produce solar energy in the desert, for example, in North Africa, and to transport the energy via hydrogen to Europe back again. One of the most recent famous works on this was by Jeremy Rifkin in the year 2002. Jeremy announced the hydrogen economy, and he wrote that it presents the clearest, most comprehensive case for moving ourselves away from the destructive and warning years of the oil era towards a new kind of energy regime. Let's say a little bit squirrel work was launched in 2003 by the European Union. It was called the European Union Roadmap on Hydrogen. And maybe this was one of the major failures in EU energy policies that happened so far. First, it said, move from a fossil fuel-based economy up to 2050 to a hydrogen-oriented economy. So fossil fuels are a primary energy source, hydrogen is a secondary energy carrier, so this was not fully logical. And they announced step by step what should happen. And for example, today in the year 2020, we should already have the interconnection of local hydrogen distribution grids, significant hydrogen production from renewables, including from biomass. Actually, we have none of these. And on the fuel cell side, we should have low-cost, high-temperature fuel cells in commercial, already in micro applications. Okay, today we are far away from this. And the EU also presented a nice figure, the vision of a hydrogen-based energy system, where you can see hydrogen grids along with CO2. CO2 may be captured from the production of hydrogen in fossil power fuels. These grids are abundant everywhere and connect the generation plants, hydrogen production plants, and finally filling stations. How does it look today? Global hydrogen energy use is dominated by ammonia, about 55% in 2018, and in refineries. The sources today for hydrogen production are about 2/3 is natural gas, next are coal and oil, and finally about 5% only from electricity. Now you can see here what is the expectation. On the left side we have the technologies and sources, biomass, hydro, but also nuclear, natural gas. And in addition, the thinking about carbon sequestration. On the right side, we have major applications such as transportation or distributed generation. And for the future, we would say, in addition, industrial processes. So the chain is simple. We have primary energy sources. We produce hydrogen. It has to be transported and stored somewhere. And finally, we will apply it to produce several services, such as, for example, mobility. In the next slides, you can see an overview on major hydrogen production processes, but I will not go into the detail. So you have the opportunity to download this file afterwards from the conference homepage, and there you can see then all these details. But it is important, primary method first. Thermal processes are steam reforming, gasification, pyrolysis, and we may use natural gas or biomass. The stage of development is, I would say, we do not have really commercial available technologies except steam reforming, but even this technology is still pretty expensive. Electrochemical methods are electrolysis, photoelectrochemical, and it is also on a level which may be improved, maybe developed further, especially also again with respect to economics. And we have the options biological, photobiological, but these are still in fundamental research stage. As already mentioned, we have now some possible electricity generation from renewables, and we might use this electricity in the process of hydrogen production and re-electrification. But however, in this chain we have many conversion steps, and finally the efficiency is rather low, overall efficiency of the system, 27 to 38% about. Another option is, of course, to use it in electric vehicles, the electricity, and to use hydrogen in a fuel cell car. At the end, it would even be possible to do some methanization, but however, again, in this case, the overall efficiency will finally be rather low, about 20 to 35%. If we look at the economics of hydrogen, first we look at the costs. And here you can see current situation. We have on the left side gas reforming, large and small. Today, the costs are about 4 to 6 euro per kilowatt hydrogen. It is a little bit more in US dollars, about 4.5 to 7. For electrolysis today, we are in the range of, let's say, 9 to 11 euro per kilogram. This is about 10 to 12 per dollar. For the future, the expectations are gas reforming will not become much cheaper, especially if we also consider an CO2 price. And on the other side, the prices for the electrolysis might go down significantly. Also, if we have available, as said, cheap electricity at times when it is abundant, when solar photovoltaic, for example, is available in abundance. And in Europe, this will maybe happen in the next years, because as seen in this figure, today renewables are the primary energy source, the energy source for electricity generation with the highest magnitude since about 2013, and it is mainly due to increases in electricity from wind and from photovoltaic plants. How does such a production generation pattern look like now? Here you can see an example over a week. We have violet demand load, we have blue hydropower, red photovoltaics, and green is wind energy. And we can see at sometimes we have more renewable production than demand. At other points of time, we have less renewable generation. If we look now how it looks over a year, we can see in summertime we have substantial excess generation. In winter times we have some additional sources needed. If we do classify now these profiles we have over a week, over a year on an hourly base, we see that we have curves like this, where sometimes we have under coverage, sometimes we have a surplus due to excess generation. Now, let's look what we can do in this area of excess generation. Of course, it does not really make sense to store every peak, so we will have some non-feed-in of peak power, some shedding. Then we will have prices very low, which might be used in direct marketing approaches. We may also use some load increases by demand-side management in a technical way. Smart grids might contribute to, let's say, shift electricity from PV, for example, from one voltage level to another. And then we have the issue of storage. But now I come to one of the crucial terms. This is full load hours. So regardless which storage we use, it has to have a reasonable number of operation hours. And here in this figure, you can see on the horizontal axis, we have full load hours. On the vertical axis, we have euro per kilowatt hour. And we have three types of storage. First, pumped hydro will operate between 1,000 and 2,000 hours. We have the battery, which will operate below 600 hours. And finally, hydrogen, we expect to have it, let's say, at least 2,500, 3,000 hours. This is important to really ensure the economics. Another important aspect is, in this context, cost of hydrogen production. And here you see hydrogen production. We have the power on the horizontal axis, and we have the euro per kilogram hydrogen produced on the vertical axis. We see we have economies of scale. That is to say, the larger the power of the electrolysis is, the lower are the costs per kilogram hydrogen produced. Next, we look how this can be calculated using these investment costs and also the electricity costs. In this figure, we see on the horizontal axis again full load hours. On the vertical axis, we have the costs in cent per kilowatt hour. Blue curve shows the price. These are the marginal costs. If we look at the average costs at a certain point of time, we obtain the red curve. And if we look here at 4,000 full load hours, we have a price of electricity costs are 2 cents per kilowatt hour. Now we take these costs and add the investment costs, then we obtain the total costs for a large electrolyzer plant of about 2 megawatt. We can see here, for example, operation time only 1,500 hours, we get 25 cents. If we have 4,000 hours, we would have here about 12 cents. This is, I would say, the current value which is broadly used. 12 cents per kilowatt hour hydrogen as a cost. Now we can compare in a first application in transport how hydrogen performs used in fuel cell vehicles. In this figure you have on the bottom gasoline, then we have gasoline hybrid, and we have some battery and range extender vehicles. We see the hydrogen-based fuel cell vehicles are most expensive, followed by the battery electric vehicles and the other electric ones. One hot issue currently discussed is the color of hydrogen. What does it mean? It means, do we use green hydrogen from renewables? Do we use blue hydrogen, mainly from natural gas with CO2 sequestration? Do we use gray hydrogen, where we do not know where from the electricity comes? And In this slide, you can see on the top, on the very top, we have the green hydrogen from wind photovoltaics hydro, and in the next we can see from natural gas. What is important is if we produce hydrogen from natural gas, we do not really have significant advantages compared, for example, to hybrid or CNG in internal combustion engines. So we are at least far away from the ideal vision to have zero emission hydrogen in general. Of course, all hydrogen emissions at the place of use are zero, but not in the consideration of the whole hydrogen chain. Let's next look at some examples. Today, the largest electrolysis plant is currently built in Hamburg, in Germany, with about 100 megawatts, 2 tons hydrogen per hour. In addition, we have hydrogen buses, hydrogen locomotives, for example, in Austria, in a private railway in Tyrol. Hydrogen for ships, at least, is discussed, given the severe problems currently with environmental benignity of, for example, cruising. Next, some scenarios. We expect technological learning, especially for the electrolysis, and this is shown here in this slide. We have here the euro per kilowatt hydrogen. And you can see on the top, we have the small systems. On the bottom, we have large systems. As I have shown before, we have quite significant economies of scale, which lead to these effects. And we can see that the costs up to the year 2050 will at least decrease by about 1/3. And similar is it if we look at the kilowatt hours of hydrogen produced. Again, we have here the level of about 12 cents in the year 2020, and up to 2050, we expect a decrease of 20 to 25%. I have shown before the slide with respect to the costs in cars. If we now apply what we have just seen to car transport in 2050, we can see here that virtually all of these fuels in battery electric vehicles, in gasoline vehicles, in fuel cell vehicles are almost in the same range of costs. And today it is not possible to tell what will really happen. So policies in different countries, I make it now a little bit short. EU has launched a hydrogen strategy in this year, 10 June 2020, China already in 2019, United States already since the 1970s, hydrogen strategies, and Germany, another example, also in June 2020, provided a budget of about 9 billion euro. What now is of interest is what if hydrogen is the wrong horse to bet on? What are finally the ultimately lasting advantages of hydrogen over electricity expected? Open question, maybe higher ranges, maybe higher filling times. As said already, so far hydrogen has not delivered. What if electricity or a technology surprise turns out to win? Technologies today are not really major, especially on the conversion side for different industrial applications. As shown in one example, the efficiencies overall in these hydrogen grids, in the hydrogen systems, are rather moderate. Environmental benignity, I have shown it, is secured only under specific conditions. Overall costs are still high. Of course, CO2 taxes would provide and economics has still to be proven. Today it is not. This leads me to my final conclusions. Are the technologies ready? How far? How to produce huge quantities of the renewable electricity? Or will the Western countries rely on imports? From which countries? Can hydrogen survive in a competitive energy market? As already said, the costs are still high. Or is it necessary to provide regulatory interferences? How will the infrastructure be provided? Will the existing infrastructure for natural gas be used? And finally, a basic statement regarding energy transition. In German, the word is Energiewende. We are convinced that a broad portfolio of supply and demand side technologies is needed. And if we bet on hydrogen, the question is picking winners in this context justified? I thank you for your attention.